This is the work solution for EP Sheet 5, Question 7 and Question 8. A roof measures 20 meters by 50 meters and is blackened. The temperature of the sun's surface is 6,000 Kelvin and the radius of the sun is 7.5 times 10 to the 8 meters. The distance of the sun from the earth is 1.5 times 10 to the 8 kilometers. Calculate how much solar energy is incident on the roof per minute, assuming that half is lost in passing through the earth's atmosphere. Assume the roof is normal to the sun's rays. So I've written out the normal equation we use here for these types of questions. So Q equals the area multiplied by sigma multiplied by T to the power of 4. So we know the area of the sun, it's here highlighted in blue, and we know what sigma is. It's 5.7 times 10 to the minus 8. And we can get the sun's temperature and multiply it by 10 to the power of 4, and we get this answer for how many watts the sun emits. So now that we know how many watts of power the sun emits, we can figure out how much it emits per unit area of the Earth's atmosphere. So if you think about the sun's energy radiating out, it radiates out in a spherical sort of fashion. So if you were the Earth and you were really close to the sun, you would have more energy incident upon you than if you were further away. The further you are away, the more spread out the energy is, so the less energy per unit area. So if you think about, okay, if you have a planet on one side of the sun and a planet on the other side of the sun, and they're both the same distance away from the sun, they would get the same amount of energy. That sort of thing should give you a clue as to how the energy spreads out. It spreads out in a spherical fashion, like I said before, but the amount of energy per unit area depends on the I guess not necessarily the radius. Well, yeah, sort of the radius of the orbit. So as you can see, the Earth rotates around the sun at this given distance. So if you were to create a sphere around the sun with a radius equal to the Earth's distance from the sun, that total area of that sphere is the area that the sun's energy is spread over. So if you divide the sun's total energy by the sphere made from the Earth's orbit, that will give you an amount of, well, we can say energy or power, but it will give you an amount of energy or power per unit area, and that's basically what we've done here. So we've gotten our Q from before and divided it by the area created by the Earth's orbit, the sphere created by the Earth's orbit. The next part of the problem is quite straightforward. So we've already got an amount of power per unit area, and we say, okay, this is the total amount of power per unit area that would be incident on the Earth under conditions that if there was no atmosphere involved, basically. But there is an atmosphere, so we need to take our value from before, which was 1.85 times 10 to the 3 watts per meter squared, and divide that by 2. And that will give us the amount of power per unit area on the roof. So now we have the power per unit area on the roof. We need to say, okay, how much power do we have in total? And to do that, we multiply that value by the area of the roof. So you can see here we've got 1.85 times 10 to the power of 3 divided by 2 to give us the power per unit area after it's gone through the atmosphere. So this is instant on the roof. And then we multiply by 1,000, which is 50 times 20, the roof's dimensions. And that gives us the amount of power instant on the roof. And then we can convert that to joules per minute, because we know a watt is a joule per second. So we can do a conversion then, figure out how many joules we get per minute. So the next part of the question can be a little bit tricky. So part of the roof in question 7 is covered by an array of photovoltaic cells, 0.4 meters by 0.2 meters, with an absorption factor of 0.5. The array produces an electrical output of 6 watts. What is the efficiency of conversion from light to electric power? So we know that we have 1,850 watts per meter squared power per unit area hitting the atmosphere. So if we divide that by 2, that will tell us how much would hit the solar panel. But the solar panel isn't a meter squared, and it's like smaller than the roof. So we have to multiply our watts per meter squared by the area of the solar panels. And this is how our problem's different this time from last time, basically. So if we just multiply this by 0.08, we should get a value of around 74 watts. So we have 74 watts, and only half of this is actually absorbed, and the rest of it is basically reflected. So we have here two arrows, and they represent our energy going in, our light energy. And in the second diagram here, we see that half of it's come out. So one arrow's gone in and become electrical energy, and the other one's gone out. So that might sort of illustrate to you what's going on here. So we have 72 divided by 4. Sorry, 74 divided by 2. 37. So 37 watts of light power inside. So if we have over here our equation for efficiency, and it says efficiency is electrical power out over light power in. Realistically, efficiency is just energy out over energy in. It's like a percentage sort of thing. So yeah, in our case, we're using electrical power out over light power in. So we've been told that we get 6 watts of light power out, so we could say our efficiency is 6 watts divided by however much light power we have going in, and we know that it's going to be 74 divided by 2, so that's 37 watts. So if we do 6 watts divided by 37 watts, we get 0.16, which is about 16% efficiency. So the final part of our problem requires us to go back to our original equations. So we have Q is equal to, sigma A t to the power of 4. So we're looking for t in this case, so we can rearrange this to find t. But the first thing we need to be aware of is that this needs to be multiplied by 0.5 because of the fact that half of our energy is reflected, so this is multiplied by the reflectance. But we also have to be aware that, well, we need Q anyway to solve for t, but our Q isn't just going to be the Q that we were thinking of before. It's basically the 37 degrees incident on the surface. Hopefully you can see as well that this Q being equal to 37 kind of lines up with us having 37 watts of energy going into the device, and we have 0.5 here as like a multiplier. Either way, because some of it gets converted to electrical energy, we actually say 37 minus 6, so that's 31. So if we say 31 is equal to sigma A t to the power of 4 multiplied by 0.5, we can rearrange to find t. So it's going to be 31 divided by sigma multiplied by a 0.5, and it's going to be the fourth root, I guess. So yeah, that should give you the correct answer. And the final result of this should be, I'm just going to neaten this up a bit actually. This is actually equal to about 341 degrees. And that's in Kelvin. So Hopefully that makes sense. If not, leave a comment below or just send me an email and I'll try and make a clearer video. But hopefully that makes sense.